tensor calculus. Okay, so to begin with, I'll start with the scalar function. So first we will see a scalar function. Let phi be a scalar function. Now I'm going to compute the partial derivative of phi with respect to x mu. So the partial derivative of phi with respect to x mu. If I transform the coordinate x nu to x prime mu, then the derivative in the transformed coordinate will be partial derivative with respect to x prime mu of phi. But I know that phi is a function of x nu and x nu is a function of x prime mu. Therefore, this derivative will be partial derivative of phi with respect to x nu, because phi is a function of x nu, and partial derivative of x nu with respect to x prime mu. Okay, because x nu is a function of x prime mu. Now I can write this as x nu with respect to x prime mu, partial derivative of phi with respect to x nu. Here you can see that the primed quantity is in the denominator, which means this function is a covariant vector, right? So I can write the partial derivative of phi with respect to x prime mu as b mu prime is equal to partial derivative of x nu with respect to x prime mu, partial derivative of phi with respect to x nu. So this partial derivative of phi with respect to x nu is a covariant vector. So I can write this as b nu. Therefore, we can see that the derivative of a scalar function transforms like a covariant vector. Derivative of a scalar function transform like a covariant vector. Next we will see what will happen if I take the derivative of a vector function. Okay, so consider a vector function a mu of x lambda. Okay, let it be a covariant vector. So under the transformation, it will be a mu prime. Can be written as partial derivative of x nu with respect to x prime mu a nu. Now I take the derivative of this vector function in the new coordinate system with respect to x lambda. So partial derivative of x lambda a mu prime. So I have to take the derivative on the right hand side also. So partial derivative of x lambda with respect to x nu, x prime nu a nu. So here first I have to take the derivative of this term and then I have to take the derivative of the second term. So partial derivative square of x nu with respect to x lambda x prime mu, then a nu as it is, plus partial derivative of x nu with respect to x prime mu as it is, partial derivative of a nu with respect to x lambda. If you see the second term, then it looked like the transformation of a tensor. But this first term contains a second derivative, and therefore it will spoil the effect of that transformation. Thus the first term on the RHS actually spoils the tensor nature. Therefore, the partial derivative of a vector is not a tensor. So this is not a tensor. So in Galilean coordinates, the derivative of the components of a vector with respect to the coordinates form a tensor. But in curvilinear coordinates, this is not the case. This is due to the fact that the derivative involves the difference of vectors located at different points of space. So we have already seen the definition of derivative. So the definition of the derivative will have a limit, right? So if you have a curve at one point x mu and another point x mu plus some delta x mu, then limit, let this distance be some epsilon, okay? Then limit epsilon tending to 0, x mu plus del x mu minus x mu by epsilon. So this is how you take the derivative of a vector at two different points, okay, something like this. So at different points in space, the vector transform differently because the coefficients in the transformation formula are functions of the coordinate. Therefore, in curvilinear coordinate, in order to obtain a differential of a vector which behaves like a vector, it is necessary that the two vectors to be subtracted from each other should be located at the same point in space. Or in other words, we must somehow translate one of the vectors to the point where the second is located. Okay, after this, we determine the difference of the two vectors, which now refer to one and the same point in space. So I'll give an example. For example, in flat space, you have, so consider a flat space. So you have two vectors. So the direction of these two vectors are the same. It is pointing upwards. If you have a curved space-time, something like this, and if you consider two vectors, it is not pointing in the same direction. Okay, one is pointing in this direction and another one is pointing in this direction. Okay, so direction of the vectors are different in a curved space-time. This is a curved space-time, so it is curved, something like this. So if I have a vector here, it is pointing in this direction. If I have a vector here, it is pointing in this direction. So direction of the vectors are different. So under a parallel translation of vector, its components in Galilean coordinates do not change. But on the other hand, if we use curvilinear coordinates, the difference in the components of the vectors after translating one of them to the point where the other is located will not coincide with their difference before translation. Thus, to compare two infinitesimally separated vectors, we must subject one of them to a parallel translation to the point where the second is located. Okay, so to compare these two vectors, let this be vector A and let this be vector B. So to compare these two vectors, I have to parallel transport one vector to the same point where the other vector is located. Okay, so how do I do a parallel transform? So that is the next topic. So next topic is parallel transport. So let us consider the surface of a sphere and take a vector at the north pole. Okay, so first we'll consider the surface of a sphere. So let this be the surface of a sphere. Now we take a vector at the north pole. So this is the north pole. So we take a vector here. So we know that the sphere is a curved surface. So on the curved surface, a vector will also be curved. So you will have something like this. Okay. So let us move it parallel to itself along the longitude. So this is the longitude. Okay. This is another longitude. So I am going to parallelly relocate or shift this vector like this. Okay, so the naive idea of parallel transport is to take the vector and put its tip on the arrow so that its direction is always along the south. So when we reach the equator, we move along the equator by an angle theta, keeping the vector point always in the south direction, and then move back up to the north pole. So now it has reached the south pole. From here, I have to make it move. So from the back side of this sphere, it will move to the north pole and it will come to its original position. So when we reach, so we have to note that when we reach the starting point, the transported vector makes an angle theta with the starting vector. So this is the starting vector. Okay, so after the parallel transport, when it is coming back to the north pole, and once it is on the north pole, we have to note that it is not the same as the starting vector, but the transported vector will make an angle theta with the starting vector. So we have to note that if we follow our naive idea of parallel transport, then we move around a closed curve. The initial and final vectors are no longer parallel. This is because the surface of a sphere is a curved manifold. And the parallel transport of a vector leads to new features. Okay, the starting vector and the transported vector makes an angle theta with each other. Okay. So how do I find the difference? For that, I am just considering two vectors at two different points in the curved spacetime. For example, I have this point x mu and a vector a mu. So contravariant vector, a contravariant vector a mu, and another point x mu plus dx mu. And I have another vector a mu plus del a mu. Okay, so let the difference between these 2 points or the distance between these 2 points be del x lambda. Now we subject this vector a mu to the infinitesimal parallel displacement to the point x mu plus dx mu. So I have to transport it to the other point. For example, I am transporting it like this. I am moving it, moving it, moving it, moving it, moving it. Okay, so it will not coincide with a mu plus del a mu. There is always a difference. So this is the whole point that I am talking about. In a curved space-time, if I translate a vector from one point to the another point, then the first vector will not coincide with the second vector. Okay. Now I denote this transported vector. Let this be the transported vector. Let it be a mu plus delta a mu. Okay. Let it be a mu plus delta mu. So under the parallel transport, the vector change its components, and this change is denoted by delta a mu. Okay, so how do I calculate this change? So I have to compute the difference between the two vectors. Now the two vectors are on the one and the same point. Now I can compute the difference between the two vectors. So the difference between the two vectors dA mu is given by A mu plus del A mu, that is the vector already present there, minus A mu plus del delta A mu. This is the translated vector. Now, the change in the component of A mu depends upon some factors. Okay, so this delta A mu is the change in the A mu, change in the component of A mu. That depends upon first one, how long it has traveled. So during the parallel transport, how long it traveled? Did it travel? Okay, how long did it travel? So here it is delta x lambda. Okay, so how long did it travel? Delta x lambda. And secondly, it will depend upon the coordinate system representing the metric properties of the space. So here I represent the metric properties by the Christoffel symbol mu, nu, lambda. Okay, so we will discuss more about Christoffel symbol and its definition and its properties in the next class. For the time being, just we can understand that the Christoffel symbol just represents the metric properties of the space. Now this change delta A mu also depends upon which vector is changed or which vector is being transported. So here it is A nu, right? So here it is A nu. So I can say that delta A mu, the change can be Christoffel symbol mu nu lambda, then A nu del x lambda. This minus sign is just a notation and it do not represent anything special. It's just a notation. Now I can substitute in the difference. The difference dA mu is given by A mu plus del A mu minus A mu minus Christoffel symbol mu nu lambda A nu del x lambda. Once you get the difference, the next step is to compute the differentiation. So the differentiation can be written as, this is the differentiation, limit delta x lambda tending to 0, A mu plus del A mu minus A mu minus Christoffel symbol mu nu lambda A nu del x lambda. Divided by del x lambda. Okay, so I can simplify limit delta x lambda tending to 0. I am just combining few terms, A mu plus del A mu minus A mu. So this much I am combining, divided by del x lambda. The rest of the things minus Christoffel symbol mu nu lambda A nu del x lambda by del x lambda. So here del x lambda and del x lambda will get cancelled. Okay. So limit delta x lambda tending to 0. Here A mu and A mu will get cancelled. So del A mu by del x lambda minus limit delta x lambda tending to 0. Christoffel symbol mu nu lambda A mu. So here delta x lambda term is not present. Therefore, the second term is simply Christoffel symbol mu nu lambda A mu. And here the limit delta x tending to 0 del A mu by del x lambda is the total derivative d A mu by dx lambda or d by dx lambda of A mu. Okay, so this is the covariant differentiation of a contravariant vector. So this is a contravariant vector. I have taken the covariant derivative and it is given by the total derivative minus this term. Okay, so the covariant derivative can be represented by A mu. A mu is the contravariant vector, and the covariant differentiation is denoted by a semicolon and with respect to lambda. Okay, so this represents covariant differentiation of a contravariant vector. Okay, covariant differentiation of a contravariant vector is equal to, now I have to write the total derivative. So I can write A mu, a comma and a lambda. This represents ordinary total derivative. Ordinary total derivative. Okay, then I have, see here there was a minus. Okay, so this minus, and here also there is a minus, so this will become plus. So here also it will be plus. Okay, plus Christoffel symbol mu nu lambda A nu. This is the covariant differentiation of a contravariant vector. Okay, this can also be represented as lambda A mu. So this is the covariant differentiation of a contravariant vector, and this is given by A mu lambda, the total derivative, plus Christoffel symbol mu nu lambda A nu. Similarly, the notion of covariant differentiation can be extended to covariant vector also, right? The covariant differentiation of a covariant vector, that is represented by, this is the covariant differentiation. Now I need a covariant vector, let it be A mu, is given by the same as the above one. Okay, so here you have a partial complete derivative. Similarly, the first step is complete derivative of A mu. Then here you have a plus. So when it comes to covariant vector, this plus will become minus. Minus Christoffel symbol A alpha. Okay, so this is the covariant differentiation of a covariant vector. The difference is that this plus will become minus. This contravariant index is covariant. Similarly, I can extend it to contravariant and covariant tensors of rank 2 also. Similarly, the entire quantity can be extended to higher rank tensors. So I'll just give an example of a rank 2 contravariant tensor and covariant tensor. The covariant differentiation of a contravariant tensor of rank 2. Okay, so this is the covariant differentiation. Now I have a contravariant tensor of rank 2. So I have two free indices. So when there are two indices, this total derivative will become partial derivative. Partial derivative of A mu nu with respect to x lambda. Okay, so and contravariant means it will be plus. Now I have to write the terms for both the indices mu and nu. Therefore I write Christoffel symbol mu alpha lambda A alpha nu plus Christoffel symbol mu beta lambda A mu beta. Okay, for these two free indices I have to write these terms. Okay, now covariant differentiation covariant tensor of rank 2. So this is the covariant differentiation. Now I take a tensor, covariant tensor of rank 2. Similarly, it will be the partial derivative of a mu with respect to x lambda. Now it's a covariant, therefore minus, and I have to write for mu and nu also. So two terms will come. So now I write minus Christoffel symbol alpha mu lambda a alpha nu minus Christoffel symbol beta mu lambda a mu beta. This is the expression for covariant differentiation of a covariant tensor of rank 2. Now, I can write the expression for covariant differentiation of a mixed tensor of rank 2. Okay, covariant differentiation of mixed tensor of rank 2. This is the covariant differentiation. Now I have to write a mixed tensor of rank 2. So mu. Same way, first will be the partial derivative of a mu nu with respect to x lambda. Then for the contravariant index, I'll write plus Christoffel symbol mu alpha lambda a alpha nu, and for this covariant index, I'll write minus Christoffel symbol beta nu lambda a mu beta. Okay, this is the covariant differentiation of mixed tensor of rank 2. So thus the entire quantity transform like a tensor, and this can be extended to higher rank tensors also. Okay, so the differentiation for the tensors is only the covariant differentiation. Otherwise, if you differentiate, it will not transform like a tensor. So the only way you can make it happen is the covariant differentiation, and it is done under the parallel transport. Okay, so once this is clear, then we'll move on to the next topic, that is rules for covariant differentiation. Rules for covariant differentiation. First one. So the first rule says that the covariant derivative of a linear combination of tensors with constant coefficient is the same as the linear combination of the covariant derivatives. Okay, the covariant derivative of a linear combination of tensors with constant coefficients is the same as the linear combination of the covariant derivatives. So I'll write this in the form of a mathematical expression. The covariant derivative of a linear combination of tensors with constant coefficients. Here a and b, small a and small b are the constant coefficient. Now this is same as the linear combination of the covariant derivatives. So a covariant derivative of A mu plus B covariant derivative of B mu nu. Okay. So this is the first rule. The covariant derivative of a linear combination of tensors with constant coefficients is the same as the linear combination of its covariant derivatives. Now the second rule says that the covariant derivative of a product of tensors, okay, the product can be outer product or inner product. So the covariant derivative of a product of tensors obeys the Leibniz rule. The covariant derivative of a scalar function phi is equal to its the third rule says that so we move on to the second rule. The second rule states that the covariant derivative of a product of tensors. Okay, so now we have a product of tensors. The product can be outer or inner. Obeys the Leibniz rule. The covariant derivative of product of tensors. So let this be A mu multiplied by B nu. Okay, now this obeys the Leibniz rule. The Leibniz rule is B nu as it is covariant derivative of A mu plus A mu as it is covariant derivative of B nu. This is very simple, right? Now the third rule. This we have already seen. The covariant, in fact we started with this one. The covariant derivative of a scalar function phi is equal to its partial derivative, right? This is very easy. The covariant derivative of a scalar function phi is equal to its partial derivative. Okay. Fourth rule. The covariant derivative of Kronecker tensor is 0. Covariant derivative of Kronecker tensor is 0. The covariant derivative of Kronecker tensor is 0. So we'll see the proof for this statement. Okay. So for proving this, we have to start from the definition of the covariant derivative. So here Kronecker tensor is a mixed tensor of rank 2. So I will take the example of a mixed tensor. The covariant derivative of a mixed tensor we have already seen, right? A mixed tensor of rank 2 is given by partial derivative of A mu nu with respect to x lambda plus Christoffel symbol mu alpha lambda A alpha nu minus Christoffel symbol beta nu lambda A mu beta. Okay, this is a general mixed tensor of rank 2. Now I have to substitute the Kronecker tensor. So the Kronecker tensor mu is equal to partial derivative with respect to x lambda Kronecker tensor plus mu alpha lambda Kronecker tensor of alpha nu minus Christoffel symbol b mu lambda Kronecker tensor mu beta. Now here this term will survive only if alpha is equal to nu, and this will survive only if beta is equal to mu, right? So I have to substitute alpha equal to nu and beta equal to mu. Partial derivative of Kronecker tensor mu nu with respect to x lambda plus mu alpha lambda. Now alpha is equal to nu. So in the place of alpha, I can write nu. Then del alpha nu will be 1. Kronecker tensor will be 1 minus. Now instead of beta, I have to write mu lambda 1. So these two terms are equal. Now this will get cancelled. So I will get partial derivative of x lambda with respect to Kronecker tensor of mu nu. Kronecker tensor will take the value either 1 or 0. So the partial differential with respect to x lambda of 1 and 0 will be 0 because 1 and 0 are constants. So whatever its value, this will be 0. So we have proved that the covariant differentiation of Kronecker tensor is 0. The covariant differentiation of Kronecker tensor is 0. So this is the fourth rule. The next rule says that the covariant derivative of a metric tensor is 0. So we'll have a look at the proof. For this, I consider let A mu be a covariant tensor of rank 1. Okay, then A mu can be written as G mu nu A nu. This we have already discussed while learning about the lowering and raising operators. Okay, therefore the covariant tensor of rank 1 A mu can be written as G mu nu A nu. Now I take the covariant differentiation of the covariant tensor A mu. Covariant differentiation of A mu. So right hand side also I have to take the covariant differentiation. Okay, now I apply the Leibniz rule, which states that A nu I can take outside and derivative of G mu nu plus G mu nu I can take outside, derivative of A nu. Okay, now here in the second term I can actually multiply the vector with G mu nu before taking the derivative also. So this will be A nu delta lambda G mu nu plus G mu nu A nu. Okay, so A nu del lambda G mu nu plus lambda G mu nu multiplied by A nu will be again A mu. So here we started with the covariant differentiation of A mu, right? So here these two will get cancelled. We get A nu multiplied by covariant derivative of G mu nu equal to 0. So here either the quantity in the brackets should be 0, otherwise A nu must be 0. Here A nu cannot be 0. A nu cannot be 0 because it is an arbitrary vector. It is an arbitrary vector. So it cannot be 0. If it is 0, then it's a trivial solution. I don't want a trivial solution. Therefore, the only possibility is that the covariant differentiation of G mu nu should be 0. Okay. Thus, the last rule for covariant differentiation is that the covariant derivative of a metric tensor is 0. Okay. The covariant derivative of a metric tensor is 0. So we wind up here for this day, and in the next video we will be having the importance of Christoffel symbol and the properties of Christoffel symbol. Okay, the definition and properties of Christoffel symbol. Okay, so for today we stop here.